I hope you like this seminar series, right? Okay. So actually, in this platform, we want to give you some kind of extra things. Okay. That means not apart from the regular curriculum, we want to give you some kind of something like extra things. Then we hope this will continue every month. Okay. Today I will. It's mostly related to the photonics, the quantum entanglement. Okay, everybody might be knowing that what is meant by the quantum entanglement. I will say something about the what is going on and what will be the understanding of this quantum entanglement. Something about the basics of these things. Okay, so if you look at that, so we have a long history. For example, starting from the Newtonian mechanics. And then we understand something about the scientific things. Okay, we are Newton or Einstein. So far, we have so many theories based on the physics. For example, the matter, how the matter, and then how it is in the motion, and then time, space, and then how the evaluation of the universe. Right. So these are all giving very sophisticated how we are understanding about the matter, and then we are that is what we are living on. Okay, and then year after year, there are so many developments has come. We are talking about the physics matter. That means how things are evolving. Based on that, we are keeping on understanding those things. Okay, if you look at that, so those days we are considering every matter is coined by the atoms, right? So how we are looking into the atom? Classically speaking, atoms are we cannot divide into further. And then many theories are prove that atoms are consist of a subcomponent, subatomic particles like that, and then that comes a quantum level. That means if you are something like a 10 power minus 10 beyond that, so that will be turned to be as a nanotechnology or a quantum concept. So once that quantum concepts are evolved, so many understanding about the fundamental things are very lot of rooms for that. So that means we are understanding as much as possible about the matter and then all the things. Okay, so that is why once the quantum evolution is taken place, so many all aspects of technology has been developed, and then we are about to understand many things about the nature. Right. So actually, before that, these are the fundamental things what you should know about the atomic structure. Basically, atom is nothing but electrons, proton, neutron, right? So how we are going to understand the atomic structure? Okay, there are the four important quantum numbers. That means we call it as a principal quantum number because the electrons are revolving in the nucleus. So that is coined by n, the symbol n. That is equal to, if n is equal to 1, first orbital, second orbital, third orbital. Okay, the hydrogen is the very lightest one. It has one electron and then one proton. So that the quantum number tends to be 1. If it is helium, 2 electrons, like that it is going. So we have about 118 periodic table elements. So that can be categorized like this. Principal quantum number, n is equal to 1 for hydrogen, n is equal to 118 for the biggest element. Like that, it can be categorized like that. And then angular momentum quantum number, that is denoted by small l. So we have that number, and the magnetic. Suppose electron is a charged particle, so it is moving, revolving the nucleus as well as self rotation, right? Whenever the charged particle is moving, there will be a magnetic field associated with that. So that is why we have to consider the magnetic quantum number also. So that is called the m suffix l, and then spin. Spin means self rotation of the electrons. Okay, the rotation of the electrons maybe it may be the clockwise direction or anti-clockwise directions. So that is giving it rise to be a different. These all the electronic structures, all the electron can be categorized these prime quantum numbers. Okay, that is why it is very important. We can call it as a wave function. Okay, understanding of the electronic structure is very important to whenever to study about a particular material or a particular system. And then what is in maybe it is also very fundamental thing you might know studying in the school level, the Pauli's exclusion principle, all the electrons are moving on, okay, that is actually the unit quantum number maybe. So it is how we are going to define is that, so no two electrons can have the same state. For example, if it is see, this is 2s orbital, that means that after filling one electron, the two electron will be the spin of means it is a clockwise directions. So that means the electron have this unique structure. One electron is taking out, that means a clockwise direction means next one is taking the anti-clockwise direction. That means there will be a systematic rule how the electrons are arranged in a particular system. Okay. So this is Pauli's exclusion principle, and then this is what the main difference between the classical concept and the quantum concept. Now previously, you know that classical means it is all the things are made up of all the things, all the properties of the materials or the properties of the things can be well defined by the Newtonian mechanics. The Newton's 3 laws are that will be giving you the clear evidence, and then we are understanding all the things how it is defined and then moving about. But once we are dealing with the quantum mechanics, that means some of the things we are not understand how things are working in a nanoscale level or a quantum level. Okay, for example, you know that Einstein's very famous experiments on the photoelectric effect. That experiment will give you the difference, the evaluation of the quantum nature. So there, when a light is falling on a metal surface, the electrons are coming out, right? So how the electrons are coming out? The electrons are coming out with a fixed, definite, discrete energies. Okay, so that cannot be explained by the classical mechanics. How things are. That means that there is a limitation. Okay, so that means we are not considering the nanoscopic particles. Okay, so superficially we are thinking maybe classical mechanics can be possible to explain the microscope things. So if you go deeper in the lower scale, what happens means we do not understand how things are working, how the electrons are coming out from the metal surface, and then how the energies are discrete. Okay, for example, this is we are clearly defined. So in the classical nature. And then if you are having that quantum means it is superposition of the things. Maybe what is happening, so it is we need to have a more understanding, deeper understanding of the lower subatomic particles. Okay, now this is what the quantum entanglement. What actually happens is we define the particles. So for example, if you are taking an electron, so electron is having a spin anti-clockwise direction or anti-clockwise direction, right? So we are talking about the entanglement means what is meant by entanglement. Sometimes it is toggling between how the state of the electron in a particular element or a system, that is purely based on the ambient conditions, right? Maybe it is biased with some external field, or if it is a free space. So these are all mostly involved in defining the particular electron. But in the case of quantum entanglement state, we cannot predict what is the state in between. Suppose we are taking we have studied the particle in a box, right? So particle in a box means where the electron is there. So understanding or the probability of finding a particular electron in a particular position, that is called the electronic structure. But here we do not know what is the state. It means a superposition of the state. For example, so when the electron is there in a metal, it may be at the something like a valence band. So, or if it gets some kind of energy and then goes to the higher state. So that means the electron is continuously moving. It's all related with the wave function. That means some of the system, it can be both like that. Whether it is a clockwise spin or anti-clockwise spin, we cannot distinguish it properly, right? It will be the same. You can assume it a clockwise direction, this there. If it is assuming anti-clockwise direction, it is there. Like that, it can be there. Superposition of the state is called the entanglement of the nature. That is why we are talking about the low dimension, that means a quantum level, that is subatomic level. The size is up there of 10 power minus 10 meters, where the particles are superimposed. That means if it is one atom and then this is another atom, these states are superimposed and then the electrons behaves almost similar. So here you see the spin is out and then this is also spin out. That means it is a clockwise direction. They will be having a sharing of these states. We cannot split in that. They will act as a single entity. Even though it is a two body, they act as a single body. We cannot distinguish the things. That is called the superposition of the state. That quantum entanglement is a very, very abnormal property which cannot be defined by the olden day experiments. Okay, that is why many people are interested to see how things are working on the quantum state or ultra low dimensions case. Okay, so that means we can call it as a spooky thing. Spooky means some kind of a super confusion or a superposition of the state. Okay, so the particle acts as something saying we cannot distinguish that. It may be if you are doing some kind of things, it can be a zero state or a one state, or one and the same. Okay, that is what the quantum entanglement says there. Okay, and then actually this kind of a things where we can apply. So if your quantum entanglement is a phenomenon, it's normal, happens for everything. For example, at the ultra low dimension. Okay, so what actually happens means in the classically we have to have two distinct states. That means if you want to make a analog to digital circuits, what is a digital means? It is all the numbers can be made up of only zeros and one. Okay, that means if you are giving a current, so that means if the electrons are conducting and then we have the one state. That means all the electrons are conducting, we will get the circuit is open and closed. And then if it is current is if you are off the current, then there is no flow of the electrons, then we will have no current. That means a zero state. So we have two possibilities. That means in the logic circuits we are giving current, that means the current is on and then one state, and then no current means it is zero state. That is possible in the classically, but in the case of a qubit means a quantum bit, there the state will be one and the same, 0 and then 1. It can be toggling between 0 and then. In between that, so there will be some kind of a superposition of the quantum state. That is what the quickness or the ultra fastness of the particles, which will be lead to a very fast nature of the computation process. Okay, that is why we can use it to replace that kind of a phenomenon in the supercomputing processes. Okay, so this is also how the qubit works. So this see this there's a quite large distance for the classical 0 to 1 like that. And in the case of quantum bits, these are the particles. Even though it is two different particles, we have some kind of a toggling between the 0 and 1 very fastly. That is why it is useful for the supercomputing purposes. And then if you are asking about what are the other possible advantages or the applications of the quantum entanglement, we can do it for the quantum encryption. For example, we are talking about the different versions or different applications. So it can be used for quantum encryption and then sending a data to a larger distances with a very high security. Okay. And then actually some other things. How the states are distinguished. Okay, that means we have the wave function, that is electrons are the ground state, then we can say that is a 0, and then the measurement is 0, and then in between what will be the average of the wave function. For example, 50% chances for the 0 and then 50% for the one state. Okay, but on the other hand, classically speaking, we cannot, we have the only clear state. Okay, clear state means, so we have only 1, 0 and then 1 level. But in the case of quantum entanglement condition, we will have some other in-between state also possible. So that is 50% of responses for either plus or 0, like that. Okay. So again, some of the introduction, maybe a lot of things are there. So I want to give you some kind of a basics how it will be applied in the things. Maybe you can develop your own things, how the data can be encrypted, and then the analog to digital conversion is possible. Those things are you can make a extra learning, and then you can understand the other things. What I want to say is that so how the entanglement process is occurring, and then actually it is a very recently proved that quantum entanglement is a kind of a abnormal problem, abnormal things. Okay, we clearly defined that there are different statistics in order to understand the electronic structures, like starting with the Maxwell's-Boltzmann statistics, and then Bose-Einstein's, latest one is the Fermi-Dirac statistics. These are all the understanding of the electronic structures, how the electronic transport is taking place, and the mobilities are there. Okay, now what is also, if you are going in a deeper sense, how the things are working there, if you know the function of the lasers. Laser is nothing but the photons are coming when the electrons and then holes are joined to the right. So that will be a coherent, highly coherent light sources will be coming, right, photons. Here, what actually happened means that if you look at that the quantum entanglement experiment, and the concept was proved experimentally by the function of the lasers. It is very recently, about 2004, scientists proved that quantum entanglement, the phenomenon. Okay. Actually, this is what the things. Okay. Spooky action. Spooky means super. That means a superposition of the things. For example, two entities, two atoms. So see, this is a photon. Maybe it is having the photons. Maybe laser photons are having the frequency is very unique. That means a highly coherent. Coherent means they vibrate. If you look at that, the vibrations, the photons is almost in phase with the time and then space. Spatially coherent. Okay, almost it is all the oscillations are very highly coherent. That is why we are getting a very highly directional and then very long distances. It can travel without any deviations. Right? We are having a source. It starts from a pencil of beams are going to the even up to the. We are talking about so many things, right? So what is the if you are measuring the distance between the Earth and then Moon, possible to measure by using the laser source. Okay, so that much distance the laser light can go without any deviations. Even the transmissions, that means the communications of the signals to the extraterrestrial planets, can be possible by the laser signals. So these are all basically what I am going to tell you is that so the coherent source that can be even if you separate two particles, the quantum entanglement can be valid. So that means everyone. So here, so even after they move away from each other, measuring the entanglement photon, so they will cause how they identify the partner. That means they are still the entanglement is there with a certain distances. That is a miracle thing, and then we have to identify. Okay, so where the phenomenon is means some kind of still, because what is the scientific evidence means things are there, right? We have to identify. For example, if you take a small silicon chip, so it is somebody, for a layman, what is this? Some kind of entity is there. But if you are scientifically, material scientists, oh, this is made up of silicon, can be useful for some kind of electronic device applications. Like that, they think it, and then if you go deeper way, then finally we will know about the what is the inner content of the material. For example, for silicon, if the band gap of the silicon is 1.1 electron volt, if you visualize under the high resolution transmission electron microscopy, the atoms are arranged very crystalline manner. Crystalline silicon is very important for doing the optoelectronic devices. Like that, so we will do understand the materials. Okay, so the quantum entanglement is also one of the very important. Then if you those who are working on a photonics or optoelectronic devices, it's a very important phenomenon. With that, so many developments, applications are possible. Okay, and then here actually how this is if you think about a one particular photon, so if it is a photon, for example light emitting diode, so the wavelengths, for example I am talking about one blue diode. Blue diode means the wavelength may be of the order of something like a 420 nanometer to something like a 450 nanometer, right? The wavelength band of the wavelength will be there. So so it is unpolarized. Maybe the all directions, maybe we will have some band of wavelength, but we need to have a single wavelength. Means how to do that? So we have to use for that some kind of a polarizing filter, and then we can make it with a some only particular. Suppose if I want a 450 nanometer alone, the frequencies of the wavelength of the 450 nanometer means, so it is a filter. Once the photons are entering to the filter, and then all other frequencies, all other wavelength will be absorbed, and then only we will get a particular single wavelength. That is called the polarization of the thing. So once we do that, then we can do that something like a, so the channelizing or a picking out the selective photons, and then all other photons will be collected and then absorbed like that. So these are all the very fundamental things for what we are going to adopt in a supercomputer, and then something like a quantum cryptography. Crypto means it is some kind of a virtual, that in computer it's possible. We are using it for all things for the good purposes, but some bad guys, what they will do it for that some kind of collecting some of this data. So how to protect our data? That is called quantum encryption. The administrator or those who are one do the things, they will know what he is doing, right? So this is all something like very fundamental things. Then how the binary space, for example, the number 209, how this goes like. So that means one means the on state, the electrons are conducting and then light will glow. That means the circuit is closed. And then 0 means circuit is open and then no current flow. Like that we make analog signals to digital one. Okay. And then actually this is also a comparison of the classical bit and the quantum bit. So here it is very distinguished. Maybe if you want to go in a staircase, okay, stair means if we want to go from third floor to fourth floor, we actually have to use the steps, right? So that is called the steps. One step, second step, like that we are going to the next level. And then when you are going a lift, okay, so what almost all the steps are equal. We cannot distinguish as an individual one like that. So we are using the classical view. The beauty is that classically this take very much delay, some kind of a delay in doing some kind of a calculations. But if you want to use some kind of a quantum qubit, the calculations are very easy. We are doing a very large number of mathematical or very big problem also possible by using the quantum computings. And then this something I want to show some other things. What is how we are understanding about the quantum world. So in a quantum state, how the particles are vibrating or oscillating is that. So almost it looks like a superposition, right? Almost how the electronic spin, whether it is a spin up or a down, okay, almost similar, and then it mixed up. Then we cannot distinguish which one is spin up, which one is spin down. Okay, that is called a quantum entanglement. So some kind of so this is, if you go to this lot of things are there. Check it and then try to learn more things about these things. Okay, and then here, so how solving the problems. Okay, so very fast in the sense that's what I explained. So that means one and the same, right? So it can be do very fast, and then almost this is also one of the things that is when we are talking about the particles, so we do not know whether the superimposition is how it is happening. We are talking classically speaking, the light, so the sunlight, how it is coming up, it's like a waves, right? So if we are making a very tiny things, that means if you are visualizing a very particular small portion of the wave, it looks like a particle. That means all the particles are combined, that will produce the waves. That is the duality of the wave nature. It can be a wave or it can be also a particle. Particles at a longer macroscopic level is wave. Okay, wave at microscopic level or a subatomic level, it is a particle. So it is a one and the same. It is there in almost everywhere. That is the duality of the things. And then it can be a, we cannot use it with the microscopic things. We have to have some kind of a very larger, that means a very high magnification microscope should be needed. That means we are having like scanning tunneling microscope that can up to a single atom visualization is possible. Okay, so that means we are talking about a set single electron transistors. Okay, because you know what we are using our cell phone and all, so it's matter of how much data we are storing. That means how the signals are conducting, because suppose what is electronic device, also electronic device, maybe we are using logic gates, transistors, operational amplifiers, and then so many electronic devices there. The functionality or the transport of the electrons from the one place to another place. Okay, in the case of a LED, so we have the electron combined with the hole that will giving a recombination of the charges will emitting as a photons. In the case of the solar cells, regeneration. Okay, that means a generation of the holes and electrons will giving a functional with the photovoltaic cells. Like that, plenty of things. The way the majority combinations are electrons and holes. The electrons and holes, how we are introducing, how we are handling the electrons and holes, that will give the required applications. Okay. And then actually this is a qubit, and then almost one and the same. You cannot distinguish what state. Okay. So there in classically speaking, there should be a definite gap. That means whether it is zero state or a one state. But in the case of a quantum entanglement state, one and the same. Based on that conditions, almost if you take the laser action, what actually means. So in the case of a laser emission, so we have a something like a valence band and then conduction band, right? So these are the gap. So if it is a semiconductor, what is that method? Here the electrons here, and then if you are excited here, so what will happen? The electron will be go to the state, higher excited state, and then what happens means we are keeping on provided the energy of the frequency of the supply external force should be more than that the work function, the band value. Okay. So the electron will go there and then it will be losing the energy and then coming back to the normal state like that. So if you are keeping on to that, so what will happen? We do not know whether the electron is here. There should be a equilibrium. Once after the equilibrium, what will happen? So cyclic process. The electron will go here and then emit light and then come to the ground state like that. This goes here, right? Like that. Just doing their own processes. Okay. So for that we need to have some kind of a very larger amount of imaginations or idea. So it is not possible to make that. We can say one electron is going here. But if you think about a very, for example, if you are taking a very high element, okay, for example gallium or something like a gallium arsenide. So those are the materials which can generate the lasers or can generate the light. These are only photonic materials, okay, which can emit some kind of a visible light. Okay, this is possible. Okay, but being our human, we are able to see only the visible range, right? 300 to 600 nanometer wavelength of range. Okay, there are some creatures, they can feel, they can see, for example, the owl, it can see in the night, right? Because their the infrared range, the visibility of the eye retina is that much powerful, but we are not seeing in the case of a cat. So they have like that. So that is why we are grouped the electromagnetic spectrum starting from the gamma rays to the radio waves. So that means we, the humans, are able to visualize the range, visual color. Okay, like that, so many things are there, but it's all how we are preparing. And then there are a lot of ways, because this is a very, very interesting area. That means a photonic band gap material, because everybody can, even if you are computer science or a mechanical student or electronic students, there will be a lot of chance. We can tune, we can prepare the lots of materials. Okay, for example, combination of the materials. We are talking about smart materials or the nanotechnology. We are talking about that means a combination of all subjects, where what will happen means everything is possible. That means one can say I am good at chemistry, one can say I am good at physics, one can say I am good at biology. Everything can be measures at one thing. That means all thing is possible. Everything is means we are understanding that's a functional material. Functional material means which can do any type of job. Okay, for example, we mix up the materials. Out of that, we are going to get some kind of a very our required thing. Okay, that is the thing. And then nowadays materials are different, but we have to choose our way. So a lot of things, because why some materials are very costly, and then why some materials are not at all having some importance. Okay, so because of the abundance of that, because we have a find out there are in the earth crust about 118 elements so far identify the human being. So that is that. Okay, based on that, so we can do a lot of things. Those one who take it for the electronic devices, one can take it for a polymer material. Different materials are possible. We have to identify and then have some kind of systematic studies on that. Okay, so this is the quantum entanglement. In the beginning I told you, the two things, it can be the same. Okay, that means it is possible at the same point. Okay, if you are thinking that it is a true entity, it is there. No, it is not a true entity, it is a single entity, it is also there. So like that, this possible if you are looking at the nanoscopic world, nanoscopic things. So this is a very, very important thing. Lots can be done based on. So every day technologies are coming up, and then the requirements also very enormously going on. Okay, that means so the necessity or the requirements is very maximum, and then this is a very interesting area you can go on. So for example, worldwide there are lots of enormous amount of research is going on. Quantum entanglement and then quantum cascade lasers. That means one laser. So one laser this is one laser, and then it will be coming 2, and then 2 will be 4, 4 will be 14, the 16 will be like that. Chain reaction is coming up. Okay. So quantum cascade lasers, and then also ultra brightness LEDs, light emitting diode, because that is one of the challenging area, because what we are using incandescent light or a fluorescent light, right? So for that we are using about a 230 voltage power supply, right? But this kind of a light emitting diode or a laser diode, which is operating in a very almost 1.1 volt or 1.5 volt of a biasing battery, right? So if you are using that, means you compare this normal power supply, alternating current supply, and then this only need a direct current supply, DC supply, right? So we are minimizing very large number of power, and then now we are very much, and the power consumption is a very big problem, right? So that way we can improve our energy consumption, and then this laser light and then light emitting diodes also emitting low heating, right? So that means global warming can be very much reduced. Okay, so like that we can choose here. Okay, so that's what I want to give you some kind of a small introduction about quantum entanglement. Right? This you can learn so many other things are there. And then you try to make, and then try to choose any important things and then go along with that. Okay. Thank you very much. If you have any questions, please